Launch pad, eh? Okay, right. Welcome everybody to tonight's meeting of the Astronomical Society of Edinburgh. Let me just change the slide. We're going to, I'll talk a bit about what's coming up over the next few weeks before we have our main speaker, Dr. John Davis, who's going to talk about missions to near-Earth asteroids. And tonight, Ian Smith is going to be giving us the sky in April, or his take on it. So, I'd like us first, though, to welcome some new members. And our new member, Ian Smith, you're all right. You don't have to give the sky in April. It's another Ian Smith. So can we do the usual and welcome these new members, please? Tim, Jim, and Ian. So for those people who are not familiar with the ASA, you can stay in touch with us. The best place is on our website, where you'll find links to what we've been doing in the past and what we're doing in the future. You can follow us on Facebook and on Twitter, and all of our lockdown videos are available on our YouTube channel. So what have we got coming up? For members only, on the 7th of April, it's the Imaging and Observing Group. But on the 16th of April, we have Bruce Vickery, who's going to be talking about the Venus tablets of Amisaduga. And that'll be followed by a member's scope talks. On the 7th of May, it's Planet 9 or Planet 9. So Discoverers in the Outer Solar System, by Dr. Samantha Lawyer, and The Sky in May by Alan Pickup. On Thursday note, not a Friday for a change, we have Professor Catherine Hymans on the dark side of the universe. And on the 4th of June, as well as our AGM, which will take place at the end of the meeting and will be for members only, we have the South African Large Telescope by Petri Visayan. And on the 2nd of July, Professor Giles Hammond, who did the first lockdown talk for us from Glasgow University, is going to be talking about asteroid light curves. And I think only yesterday I managed to confirm that on the 18th of June, we have a talk from Tom Field in Seattle on spectroscopy, a practical approach for amateur astronomers. Using a star analyzer grating, which is just like a screwing filter, and the software he has developed, you can do some quite remarkable things with amateur telescopes or just cameras. So that's what we've got coming forward. But tonight, it's Dr. John Davis who's going to talk to us about missions to near-Earth asteroids. So I'll stop sharing, John, and you can start.
Hello, everyone. I'll just get my screen sharing thing organized first. Here we go, I hope. Right, so if all's gone well, you should have a white screen with a few words written on it.
Yep.
Okay, so hello everyone, my name is John Davis. I'm an astronomer at the UK Astronomy Technology Centre, the new name for the Royal Observatory, Edinburgh. I've been coming to your meetings on and off for some years now, and I'm always grateful for your help at the Observatory Open Days. Obviously, we didn't have one this year because of the current situation. Hopefully, maybe we'll have one later this year, who knows. And I'd also like to thank you all for giving this talk priority over Carry On Screaming, which starts at 8 o'clock on BBC, one of the preview channels. So I'm going to try and talk to you a little bit about two missions to near-Earth asteroids which are going on at the moment: the Japanese Hayabusa-2 and the American Osiris-REX. But I'd start by just getting everyone on the same page by just talking a little bit about what exactly do we mean by near-Earth asteroids. Now, I understand you're amateur astronomers, you probably know some of this stuff already, but just to get everyone on the same page, what exactly are we talking about? If we go back to the 1980s, when I started in this game, there were a number of groups of near-Earth asteroids. We knew of only about, I don't know, 100, maybe 200 in total. And they tended to be classed into one of three classes. Now, people, you think of asteroids as mostly living in this donut between Mars and Jupiter, which we call the asteroid belt. And then there's another group that sit out in Jupiter's orbit, the so-called Trojans. But there are a number of small rocky objects whose orbits bring them out of the main asteroid belt and can cross the orbits of the inner planets. So the picture in sort of yellowy orange is what we call what we used to call at least an Apollo asteroid. It has its most distance from the sun. It's somewhere in the asteroid belt, but it comes in around the sun and crosses the orbit of the Earth before returning to the asteroid belt. So that's a potential Earth impactor, of course, because it's coming across the Earth's orbit. There's another much rarer class, which we call the ATENs. These have a semi-major axis of less than 1 astronomical unit. So the average distance from the sun is less than the average distance of the sun of the Earth. So they spend most of their time interior to the Earth. Of course, their orbits aren't exactly circular, so they can also graze the orbit of the Earth and potentially collide with us. They're the hardest ones to find because they're almost literally in the same patch of sky as the sun. So they're only really detectable in the twilight. And finally, there was another group we called the Amors, which again had their most distant point out somewhere in the asteroid belt. And they crossed the orbit of Mars, but not the orbit of the Earth. These can, however, under some circumstances, evolve from Mars crossing into Earth crossing orbits. So we have this population of near-Earth objects. We call them near-Earth objects now because we've learned over the last 30 or 40 years that they're not all asteroids. Some of them behave more like extinct cometary nuclei. So we tend to call them near-Earth objects these days. But there's a very interesting thing about these, and that is if you count the number of near-Earth objects, we know that their average lifetime is about 10 million years. In 10 million years, a typical Earth crossing or planet crossing asteroid will either collide with the sun, it will collide with a planet, mostly the Earth, or it will have a close encounter with the Earth or Venus and be ejected from the inner solar system. Now, we know of several hundred of these things, thousands now, in fact, and if they only have a lifetime of 10 million years, then one of two things must be true. One is we're seeing a tiny remnant of what was once a massive population, or they're constantly being replenished. In fact, we know that they must be getting replenished because the original population would have to be unfeasibly large if the number we see today was just a tiny fraction of survivors. So we know that on a timescale of a few million years, all of the current population of near-Earth objects will be ejected, but they will be replaced by other objects from the main asteroid, mostly from the main asteroid belt. So how do they get here? Well, you might think, indeed, if you watch the movies, this is what they will try to tell you, is that asteroids have collisions in the main belt and they seem to get bashed into Earth crossing orbits. But unfortunately, that doesn't work. The energy you need to divert an object from an almost circular orbit in the asteroid belt into a fairly elliptical orbit that crosses the Earth is so large that if you delivered that energy in the collision, you would pulverize the asteroid, you would smash it to dust. So there must be another way of getting objects from the asteroid belt into these Earth crossing orbits. And there is. If you look at the number of asteroids compared to their distance from the sun, you might expect a sort of smooth bowler hat type distribution with a big bulge in the middle, but that's not what we see. We see, as you can see in this picture, that there are distances from the sun, semi-major axes, which there are almost no asteroids at all. And it turns out that those areas are swept clear because if you're orbiting in one of those distances, then the orbital period of the asteroid is an exact multiple or a fractional multiple of the orbit of Jupiter. So Jupiter goes around twice, the asteroid goes around 3 times. They're at the same relative position every few orbits until the gravity from Jupiter is constantly pulling in the same direction. And what that does is it clears out some of these areas of the asteroid belt, and it throws objects into these Earth-crossing orbits. So these things are called Kirkwood gaps because they were discovered by a chap called Kirkwood. And it's much easier. You just have to nudge an asteroid. So if you've got something at, say, 2.45 astronomical units, you only have to nudge it a little bit to knock it into the 3-to-1 resonance at 2.5 AU. And then Jupiter's gravity will flip the thing up and send it into the inner solar system. So you don't have to deliver all the energy in one big punch. You just have to nudge it enough to put it in a Kirkwood gap, and then Jupiter's gravity will do the rest. And there's another thing about the asteroid belt which is important to our story here, and that is that the asteroids are not randomly distributed. Even within the structure of the Kirkwood gaps, asteroids are not randomly distributed. This is a different plot. This is the distance from the sun along the bottom, but now I have the orbital inclination plotted up the side. And what we see is the asteroids are not randomly distributed. There are distinct groups of them. So there's the Hungarias and the Phaseas in the top left-hand corner. These are large numbers of asteroids which have very similar orbital properties. And what we believe that has happened here is these are families of asteroids created by the disruption of a single larger asteroid sometime in the last few billion years. So these asteroid families result from asteroids which have formed, grown quite large, and then subsequently been disrupted. And that'll be a part of our story when we talk about these near-Earth asteroids, which we're going to look at tonight. So the first of the two missions I want to talk about is Japanese mission called Hayabusa-2. The clue's in the name, it's the second one. The original Hayabusa mission was sent to asteroid Itokawa. And those of you who've been to the ROE during an open day will probably have seen me wandering around with a 3D printed model of Itokawa. Itokawa was a great success, but several bits of it didn't work. Its landers didn't land, and its sample grab mechanism barely collected anything. So an improved version, basically similar but with some improvements, was commissioned as Hayabusa-2. So its objectives are to rendezvous with a near-Earth asteroid, drop some landers. I call them hopping landers because they're not really rovers. They don't rove. They don't have wheels. They just jump. And also to collect samples and to return those samples to the Earth. The selected target is this one, number 162173 Ryugu. It's a C-type asteroid, so it's carbon-rich and it's relatively unmodified. If it were to land on the Earth, it would be a carbonaceous chondrite type asteroid. It's an Apollo asteroid, and it's one of the subgroup of the Apollos that has, in principle, a chance of crashing into the Earth, though it's classified as being a potentially hazardous asteroid. That's what PHA means. It's not on a collision course right now, but its orbit could evolve over the next few hundreds or thousands of years to bring it into a collision with the Earth. There are quite a lot of these PHAs. None of them are currently known to be on a collision course with the Earth, but they are potential Earth colliders. Its size is about 900 meters in diameter, so a little over half a mile, and it rotates in 7.5 hours. For those of you who are interested, the numbers about the orbits down there underneath. So Hayabusa-2 was launched by a Japanese H-2 rocket in December 2014. This is an indigenous Japanese launch vehicle launched from the mainland, one of the islands off Japan. The launch windows are set not only by celestial dynamics, but also by the fishing season, by the way, because the first stage lands in the sea and they can only launch at certain times of the year when the fishing fleet aren't at sea, because that's the same area of sea as the fishermen like to be. And it followed it's fairly conventional these days for one of these missions, and you don't fly straight to the target. It's launched from it goes around the sun once or twice, it has an encounter with the Earth, it picks up energy from the Earth, from an Earth flyby, which flings it further out, and eventually brings it to arrive at the target, in this case, about 4 years after launch. So it's launched in November 2014, It comes past the Earth a year later in 2015, and it finally arrives at the asteroid in July, a little under 2 years ago, a little over 2 years ago. So the spacecraft puts itself in what the Japanese like to call its home position, which is about 20 kilometers from the asteroid. So that's 20 or 25 asteroid diameters. And the spacecraft uses this home position to do systematic mapping of the whole object. So it sits out here at 20 kilometers and it photographs the whole asteroid as it rotates. And when they want to, they bring it down closer in for high resolution imaging and to practice their sample grab technique, which we'll get to in due course. And what turns out fairly early on is that, well, it's not round, unsurprisingly, it's not round. But what is surprising is that this asteroid has a very large number of boulders on it. It's not really a dusty object with a few rocks. It's a very, very rocky object. And that creates an immediate concern for the engineers because they designed their spacecraft to do a sample grab on something which has relatively flat areas, which are relatively dusty, and not on something that's a boulder field. From the home position, the spacecraft maps out the whole of the asteroid, and this is an extract from a quite excellent paper in Science magazine. It's a well worth a read. It's not very technical. No, it's not too technical, and it's a pretty good description of the global properties of this object. So the top picture shows the whole of the surface. It's one of these projections, and like maps of the Earth, it gets distorted as you get near the poles. It gets particularly distorted because this isn't even a sphere; it's more of a diamond. So the apparent concentration of craters around the equator is a consequence of the way the map is projected. But they do detect a number of craters of various ages. And down the bottom right is this thing called Otohime-Saxum. Now, this is a boulder. It's essentially just a large boulder. And this created something of a conundrum because they wanted to name it, but there was no naming convention for boulders. I mean, there's a naming convention for craters. There's a naming convention for cracks in the surface. We call them rills. There's a naming convention for mountains. But there was no naming convention just for boulders. So they had to go and invent one. And they decided that you could name it if it was more than a few percent, I forget the number, 5% or 1% of the diameter of the object in question. So this boulder, Otohime-Saxum, which means saxum is the Latin word for stone. It was big enough to get a name, and you can see it on the picture B. It's got the red arrow pointing at it. It's quite large compared to the object itself. Picture B also shows in a string of yellow dots, the rotation axis is from bottom right to top left. Rotation axis, so it's spinning around a diagonal, and that has an equatorial bulge, which is marked out by those yellow dots. And it also has marked out by the blue arrows a trench or a valley, so to say. And the final picture on the right, box C, just shows some stones, some boulders, and the little arrows mark the direction in which dust is drifting. And this made me laugh, so because I've actually got the copy of the paper. I'm going to read you out the caption for this. Okay. So this is figure C. Asymmetric regolith deposits on imbricated flat boulders on the northern slope of the circumequatorial ridge. The small yellow arrows at the edges of the regolith deposits indicate the direction of mass wasting. The large yellow arrow indicates the current geopotential gradient from high to low. The direction of the geopotential gradient is consistent with the mass wasting. Now, what I think that actually means is that dust rolls downhill. So that's what they're saying here, is that the gravitational potential is such that the dust is just drifting down towards the area where its gravitational potential is the lowest. But the most exciting thing about this was these sample return object and the objective of making landers. So these there were two of them. Well, in fact, there were several of them. The Minerva landers were built by the Japanese themselves. The Mascot lander was a joint project with the Germans and the French, which was carried on this Japanese spacecraft. So let's look at the Japanese ones first. It's called Minerva-2 because the Minerva-1 craft were carried on Hayabusa-1. And it's called Minerva-2-1 because there are in fact two different Minerva landers on this spacecraft. To give you an idea of size, these are about the size of a dinner plate. So they're 18, I think they're 18 centimeters in diameter. So that's a couple of 7 centimeters high, and they weigh a kilogram. So we're looking at a bit smaller than a dinner plate here. They're got solar power, and they move because they've got inside them a little widget, which is a bit like the vibrator in your mobile phone. The gravity on Ryugu is so low that you don't need a lot of energy to move things around. So just putting your phone on vibrate is enough to make these things leap up off the ground and then randomly move and land somewhere else. They were deployed. These are some pictures taken from these rovers on the surface of the asteroid. Now, you may notice, I certainly did, that there are no scale bars on these pictures. And I have tried several times to get pictures with scale bars on, because without scale bars, it's difficult to know exactly what you're looking at. And I've not been able to. And I suspect the reason is that the science team want to keep that sort of information in their back pocket until they've had a chance to write their papers. If they put the pictures on the internet with scale bars on them, then every man and his dog will download the pictures and start doing their own analysis of them. But you can see that the surface is clearly, my guess is we're looking here at pebbles and tennis ball sized stones rather than anything much larger than that. But you can see that the surface is very, very rocky and not very dusty at all. Now, these rovers survived a remarkably long time. One of them, 1A, lasted 36 Earth days. Now, Ryugu rotates in about 7 hours, if you remember. So that's 113 rotations of the asteroid. And during that time, it returned over 600 pictures. Rover 1B lasted only 3 Earth days, 10 sols on the asteroid, but still returned 39 pictures. So that's a pretty impressive piece of work for something the size of a dinner plate. This is the Mobile Asteroid Surface Scout, or Mascot. Again, for scale, this is about 29 centimeters on the long side, so that's just under a foot, and 20 centimeters high, and it weighs 10 kilograms. So it's a bit smaller than a microwave oven, but not much. A bit bigger than a shoebox, a bit smaller than a microwave oven. And this was dropped from the mothership from a height of 51 meters, so what, 150 feet, 160 feet or something. And it takes 6 minutes to fall. The gravitational field of the asteroid is so weak that it takes 6 minutes to fall at 51 meters. And here's a picture of the Mascot after it's released from the mothership, falling towards the surface. I guess most of us are old enough to remember when pictures from space were rare and grainy, and you were lucky if you saw anything. Of course, these days, with the modern camera technology, we can just do remarkable things. So here is a picture of Mascot falling away. And the next one's even more remarkable. The picture on the left shows the shadow of the Hayabusa spacecraft, and then the box in blue is enlarged on the right. And in the box in blue, and on the right-hand image, you can see the image of Mascot itself, of about 10 pixels, and you can also see the shadow of the Mascot on the surface as it falls towards it, as well as the shadow of the Hayabusa spacecraft itself. And this is a picture of the surface taken from Mascot just a few seconds before touchdown. And the next little montage shows what happens when it gets there. So the mascot stuff, you look at the top picture, it starts in the bottom right-hand corner. If I was with you, I'd have a pointer and I could wave my laser around, and then moves diagonally up towards the top left. At point D, it takes the photograph, which you can see in the middle center at the bottom. If you look at the picture in the middle center, you can see a stone. There's a stone that looks about the size of a pork chop, looks a bit like a pork chop, and you can see that in the top picture, just about where the letter D is. Then it takes another picture from point E, which is shown in the bottom right, and then it makes its first contact with the surface by crashing into a stone where it says CP1. If we flick to the middle strip of the picture here, it hits this stone, and it takes a few minutes to bounce across the surface before it finally lands and starts taking scientific observations. Now, there's a German, I've got a press release here which tells you exactly what happens in a sort of second by second. It's its first position, it's daylight, and they start taking scientific measurements, but they soon realize that the probe has landed upside down, so it can't execute its full science program. And it has a little writing mechanism which springs an arm out and flips it over. So that's what happens after the first science cycle. It says first relocation. So this spring-loaded arm flicks out and flips the thing over. So now it is the right way up, and it can make its proper science measurements. Then it goes into night again. Then the next day it comes light again. It has time for a few more observations, and then it finally shuts down. And it has to shut down because, excuse me a second, it has to shut down because this is only running on batteries. It doesn't have any solar power system or anything like that. It just had a battery system, and it was good for 16 hours, they estimated. It actually lasted 17. When it went into night time again, it was still working, but it didn't wake up. The batteries were flat by the time the sun rose after the third night. Now this is quite successful. There's a picture here which does have a scale bar on it. It's a close-up of the surface from Mascot. And the red spot is the area which was sensed by a thermal imaging instrument, which tells us that the surface here has high porosity, so it's dust with lots of gaps in between, and it has very low tensile strength. It's really just loosely piled up dust. So then we get onto this sample, the attempt to grab a sample. Now this was done, was attempted before on the previous Hayabusa. On the previous Hayabusa, the landers were dropped in the wrong place and they missed the asteroid completely. Now the sample attempt is made in February 2019, and it's the same technique as they used on Hayabusa-1, only this time it worked a bit better. So this is how it's supposed to work. First of all, they drop a small object called a target marker. That's the little blue thing you can see in the left-hand side of the screen. That's just there to help the main spacecraft navigate its way down to the surface. Remember, although this is a near-Earth asteroid, it's not that near, so there's a significant time delay as the signals go to the asteroid and come back again. So you can't fly this thing down to the surface using a joystick. It all has to be done fully autonomously. And to help it navigate to the surface, it drops these target markers first. And then the idea is it descends towards the surface, and sticking out the bottom is essentially an upside down trumpet. That trumpet is designed to push itself into the surface soil, at which point a small metal ball bearing is fired down. And that's the idea of that is to throw up dust, which then gets caught in the horn of the trumpet and bounces up into the spacecraft to be captured in the sample retrieval mechanism. And that's what went wrong on Hayabusa-1. They did the touchdown, but the ball bearing didn't fire, so no dust or very little dust was thrown up into the sample collection chamber. However, this time it all worked pretty well. This is a picture of the target acquisition site taken just before the sample grab on the way down. And if you look at the bottom left-hand corner, there's a boulder which has got a big split in it, and then it's got a little rock to the left-hand side of that. If you kind of fix your eye on that, and then there's another stone up at about 1 o'clock. That's about where the sample is going to be grabbed from, about pretty much the center of this picture. So that's the before image. It goes down, it fires this ball bearing into the dust, and then it retreats. And here's the picture taken as it comes back up again. On the left-hand side of the picture is that boulder with the split in it, and you can clearly see in the center of the picture an area of disturbed dust where the sample grab's been made. Now, I did have a video of this, but the videos tend not to work very well over Zoom, so I didn't put it in. But it's quite a dramatic thing at the moment of touchdown. There's stuff flying everywhere for a few seconds as the sample grab goes on. Now that's very good. So they've successfully grabbed, or they hope to have successfully grabbed the sample of asteroid dust, but it's asteroid dust from the surface, which has been exposed to the sun for many tens of thousands, maybe millions of years. And it would be interesting to know how much of that has changed due to the weathering effect of the constant sunlight and the solar wind and the cosmic rays. So this is a concept called space weathering, which was highly controversial when it was first put forward, but is now accepted, and that is that the surface does age. So if you really want a pristine sample, you have to dig below the surface. And so this is how they decided to do this. They first released this thing called the Small Compact Impactor, which is the thing on the left. Now this is the shaped charge. Most of you probably don't come across shaped charges very often, but it was discovered quite a long time ago that if instead of having a ball of explosive, you shape it into a cone or a teacup shape, when you ignite it, all of the energy is directed in one particular direction rather than blasting out everywhere. And that's the principle behind the warhead of a bazooka or an RPG, anti-tank rockets, which you see people wandering around with in guerrilla wars. When the shaped charge explodes, all the energy goes in one direction. Now, in the case of an RPG or a bazooka, you want the energy to burn its way through the side of the tank. But in this case, the shaped charge is used to blast a lump of copper from the impactor directly at the surface. So although the news stories at the time said that they had bombed the asteroid, that's not quite true. The explosion occurs at some altitude, and it's a lump of copper blasted by the shaped charge, which flies down and hits the asteroid itself. To see if it's worked, they also released a small free-flying camera. That's in the right-hand picture. It looks like a Coke can with a pencil sticking out of it. That's a camera whose sole job is to look at the asteroid to see if they can see where the impactor landed. And after the impactor was released and before it was detonated, Hayabusa went and sneaked away and hid around the far side of the asteroid just to make sure it wasn't hit by any debris caused by the impactor. And amazingly, it works. Here's the SCI release. Again, there's cameras on Hayabusa which can return very good pictures. So there's the impactor being released and hovering in space, waiting to explode its lump of copper down to the asteroid. And here's a picture from that free-flying camera. The bottom picture is the main picture, but up in the right at the top, almost just to the left of the top center, you can see a plume of material escaping from the asteroid, and that's magnified in the inset top right. And you can actually see material flying off the asteroid, so that tells them that this impactor has indeed struck the asteroid and has indeed ejected some material. So then you have to find it. So after waiting a few days for any dust to settle, Hayabusa then maneuvered itself back around and went looking for the crater created by this impact. And they do eventually find it. Here's the before and after images. This time they're the same orientation, same scale. You can clearly see this rock to the right-hand edge of the picture. It looks a bit like the logo on Captain Kirk's shirt on Star Trek. Unsullied in the first picture, and right next to it in the second picture is a hole some meters across, blasted by this copper projectile. So they then maneuvered their spacecraft down to repeat the touch and go sample grab, and this time aiming to pick up some of that material which has been ejected from the crater, and so has come from below the surface, and so hasn't been exposed to solar radiation for hundreds of thousands or millions of years. So then in principle, they can compare the two samples and see how much space weathering there's actually been. Here's a close-up of the landing site. You can see the craters in this thing called CO1, and it's about 10, 20 meters maybe of disturbed material. Here's the second attempt at the sample grab. There's the trumpet. There's the like this thing that looks like a horn as it goes down. And that's the moment of impact. And you can see stuff flying everywhere. This is a still from a video, but you can clearly see stuff flying everywhere as the bullet is fired into the horn to stir up the dust, and then the thrusters fire to pull the spacecraft away again. So both of these sample grabs went extremely well. There was in fact resources on the spacecraft for a third attempt, but they've decided not to make it on the grounds, I think, that they got a before and they got an after sample, and it wasn't worth risking another touch and go. They'd rather quit while they were ahead, so to speak. So what does all this tell us about Ryugu? And I've got to actually, as you would guess, at the vital moment, I forgot the name of these things, but never mind. The chemistry of the surface, as determined by the images and the spectrometers on the spacecraft, suggests that the surface of Ryugu is composed of material which has been altered by contact with water and then dehydrated. Now, there are several ways of doing this. The easiest one is if the asteroid, if the parent asteroid, the original asteroid from which Ryugu is going to forms in the early ages of the solar system, it traps quite a lot of aluminum-26, which is a radioactive element, which is formed when the sun is young. This aluminium-26 is trapped inside the asteroid. As it decays, it generates heat, and the middle of the asteroid is warmed up, and so you get this aqueous alteration takes place, and then the heat that's generated by the decay of aluminium-26 dehydrates the asteroid. Now, you could also dehydrate the asteroid by having large numbers of impacts. Obviously, an impact delivers quite a lot of energy, but it only delivers it to a single point. It's quite hard to toast the whole inside of the asteroid by just bashing it repeatedly from the outside without breaking it up. So the best bet is that this aqueous alteration of dehydration takes place by the radioactive decay of trapped aluminium-26, which in turn means that the original object, must have formed quite early in the solar system's history. What seems to have happened then is that the original parent body was smashed by another asteroid to form one of these asteroid families. Now, remember, I mentioned asteroid families at the beginning, where you have a number of objects with very similar orbits. So the parent object seems to have been impacted by another asteroid and disintegrated, forming one or more families of asteroids. Because they're all in the same patch of space, they've all got very similar orbital elements. These objects can then bump into each other gracefully and gradually reaccumulate. So you then make yourself another asteroid, which is made up of bits from the parent. And because the parent was differentiated, so it had a crust and some different material inside, but because it's been smashed to pieces and then reassembled, the daughter asteroid doesn't have to have a nice homogeneous surface. It can have bits of the middle and bits of the outside all mixed up together. So this seems to have happened, and possibly a second impact, which broke up the the daughter asteroid, and formed another cloud of dust and debris, which itself then reformed. So Ryugu would be a granddaughter asteroid, which is the remains of the smashed up daughter, which is the remains of the original much larger asteroid. And the chemical composition from the spectrographs does match a couple of asteroid families in the region of the asteroid belt from which we think Ryugu came. I've forgotten the names of them and I can't find a piece of paper I've written them, but it's not important to know exactly. But it's quite consistent with this whole idea that a big asteroid forms, gets disintegrated, reassembles, maybe gets disintegrated again, reassembles yet again. And so it is an escape from an asteroid family. Hayabusa departed the asteroid in November 2019, and just around Christmas time last year, the mothership flies past the Earth. It releases the sample return canister. It then thrusts to avoid crashing into the Earth itself, and the sample canister performs a re-entry. As you can see, this is a gentleman carrying it. It's about the size of an ice bucket. And it lands in the desert in Australia in the Woomera missile range in December 2020. By coincidence, within 24 hours, the Chinese Chiang mission had returned lunar samples. So almost literally within 24 hours, we got extraterrestrial samples from two different celestial bodies. What now? Well, the sample was successfully returned. It's been returned to Japan. I think they've already started opening it to find out what's inside it. But the mothership's still in pretty good shape. It's actually propelled by ionic thrusters. These are thrusters which generate low power but can operate over long periods. It had 60 kilograms of fuel and there's still 30 kilograms left. So there is the potential for an extended mission. Obviously, they can't do another sample grab because there's no return capsule anymore, but all the rest of it is still working, the cameras and so on. So there's a proposed mission extension which uses the gravitational flyby of the Earth to send it in the direction of this object, 98943, originally known as 2001 CC21, where it will arrive in July 2026. And this is a picture I just grabbed off the web this morning, actually, showing a sort of simulation of the asteroid target. It's about 1 kilometer in diameter, and this is Mount Everest, at roughly the same scale. So you can see how these things are not even the size of a mountain. It's roughly 1 kilometer in diameter, and its semi-major axis is 1.05 astronomical units. So it's pretty much the same. It's another Earth crossing asteroid, and if that's successful, and there's still fuel left, then the spacecraft will be redirected to another Earth flyby, and then another Earth flyby, and that will take it to its final destination. To its destination. All destinations are final. That's what destination means. That will send it to its final target, 1998 KY26, where it will arrive in July 2031. What do we know about KY26? Well, not very much. It's pretty small. A few tens of meters at most. So this is not even a mountain. This is a building. This is a flying building. It's not even a skyscraper, really, is it? It's a 5-story building or something like that. It's roughly spherical. It's been observed by radar from Arecibo before it fell down. Its spin period is very, very rapid. It's about 11 minutes. Now, this is a phenomenon which we see in near-Earth asteroids, and that's which tells us that most near-Earth asteroids are not solid objects. There are no rapidly spinning near-Earth objects. Most of them spin in more than 2 hours. And what seems to be the reason is if they spin faster, if they want to rotate in less than 2 hours, they have to spin so quickly that there isn't enough gravitational attraction to hold them together, so they disintegrate. These very fast rotators are very small, so we think they must be essentially individual boulders, individual shards of a disintegrated rubble pile. So if you were to spin Ryugu up, make it spin faster, it would rapidly fall apart. It would eventually reach the point gravity wouldn't hold it together and it would fall apart. And that's probably what KY26 is. It's a shard from a disintegrated near-Earth asteroid. But it's probably fairly round because the photometry, such as there is, doesn't show a lot of variation, which you'd expect if it was a funny shape. So we know very, very little about it, but if they pull this off, and of course we'll have to wait 10 years to find out, if they pull this off, it'll be a remarkable achievement and presents severe engineering challenges. They are talking about attempting a landing. Now, at this point, the word landing and the words controlled crash become very blurred. Ryugu has no landing gear, and the thing is spinning too quickly to drop another target marker because the centrifugal force is likely to throw the target marker off if it lands. So they may well decide that once they've got into orbit and taken all the pictures they can, they will attempt a controlled crash just to get the engineering data that tells them how to do this thing if they ever want to do it again. So there's still a lot to come from this mission, apart from the scientific analysis of the samples. But there's still, in principle, 2 more flybys and a 10-year mission ahead of us. So that's Hayabusa. By coincidence, the American Space Agency, NASA, have a asteroid sample return mission on the same timescale, and it has this rather contrived name of Osiris-REX. Osiris is an Egyptian god, and you can see the spelling out of this rather contrived acronym: the Spectral Interpretation, Resource Identification and Security Regolith Explorer. That's part of the justification for this. Is if we're ever going to deflect a near-Earth asteroid that's on a collision course, we need to know what they're made of. It was selected about 10 years ago as part of the New Frontiers series, which are supposed to be relatively cheap. And the primary objective is an asteroid sample return, same as Hayabusa, but no rovers or landers this time. And here's a picture of the spacecraft on the right. You can see how big it is. It's a decent sized thing. There's some people standing around it. Its target is 101955 Bennu. I have a 3D printed model of this thing, which if I was with you in person, I would now be holding up and probably passing around. Bennu is another potentially hazardous asteroid with a small possibility that it might impact the Earth sometime in the next 200 years. It's about half the size of Ryugu, 500 meters, and it rotates quite quickly in 4 hours. And there's the orbital data for those of you who care. Osiris-REX was launched in 2016 on an Atlas rocket, and it does the same sort of trick as Hayabusa. It flies away from the Earth, then it comes back to the Earth to get an Earth gravity assist, which then flings it out a little bit further away from the Earth to rendezvous with the asteroid. It arrives in December 2018. It first makes several flybys at a reasonable distance to get some decent mapping and also to get the gravity field well understood. And then on New Year's Eve, wasn't it, 2018, it finally puts itself into orbit. Now, this is a 500-kilometer object, and the orbit is only 1.75 kilometers from the center. So it's only its distance above the surface is only just over a kilometer, over going round a thing that's 500 kilometers and just over a kilometer going round something that's almost 500 meters in diameter. So it's pretty clever navigation. And you see 2 things straight away. First of all, it's covered in rocks, just like Hayabusa's target. It's very, very rocky. And just like Hayabusa's target, it's got some big boulders. You can see one on the left-hand edge, and you can see one bottom right. So it's very rocky, and it's got some big boulders on it. Here's a rotation movie. You can see how those big boulders stick out when they're seen on the limb. And it's a problem, and grabbing the sample is going to be a problem because, again, like Hayabusa, it was targeted on the assumption that there will be areas of the surface which were flat, 10 meters or so in diameter, flat and smooth. And that turns out not to be the case. Here's a view of the southern hemisphere. There's a big boulder highlighted there, 7.4 meters. That's about the size of a house. So, this is clearly going to be a trick to land on something that's as rocky as this. And you'll also notice that the boulders are not all the same color. There's a lot of variation amongst this material. So it looks like, again, we're looking not at an object which has been built and then had a stable life, but it looks like it's had a very turbulent past. After they'd been in orbit for a while, they were able to make a decent map, and you've got the same problem here as you have with Ryugu, that the Mercator projection doesn't work very well because it's not round. These are all rocky features, and the one I've highlighted with the black arrow is named for an Egyptian mound, and it's 21 meters, almost 22 meters, 65 feet or so high. So again, this is a big rock. But that wasn't the biggest surprise. The biggest surprise came while they were doing some of their early orbits, because they found material was actually flying off Bennu. Now, you expect, if you go into orbit around a comet, as Rosetta did, you expect comets to evolve material. You expect jets of gas and dust, but you do not expect ejecta from an asteroid that's only 500 meters in diameter. This can't be volcanism. It has to be something else. And it turns out not to happen just once. I mean, if it just was once, you might think it's a random meteor hit and we were just very lucky to see it. But actually, these ejections seem to happen fairly regularly. And they always seem to happen around about 3 o'clock local time. So what seems to be happening here is that the asteroid heats up in the sunlight, and by mid-afternoon, the surface is about as hot as it's going to get. And from time to time, the thermal stresses cause material on the surface to crack, pop, and fling little bits off into space. Most of these don't have escape velocity, so they enter a brief orbit around the asteroid and then fall back down again. A few of them do have escape velocity, and so drift away. And this might be why 3200 Phaeton, which is another asteroid which seems to have a dust trail. 3200 Phaeton is the parent body of the Geminid meteors. It was actually discovered by Simon Green and I from the IRAS data in 1983. And we always wondered where the Geminid meteors came from. We thought at first we'd found an extinct cometary nucleus, but Phaeton turns out to be a rock. And then you have the question, well, how can you make a meteor shower out of a rock? And this might be the answer, because here is an asteroid which is primarily rock, which is ejecting dust into space. So maybe Phaeton is doing the same thing. And Phaeton gets even closer to the sun, so these thermal stresses would be much larger. Luckily, these clouds of debris do not represent a threat to the spacecraft, so they were able to proceed with their sample grab. What they see from orbit, however, when they look closely, is much the same as you saw on Ryugu, and that is that some of the rocks on the surface are very different from the rocks around them. In this case, the ones are highlighted are much brighter than the material on which they're sitting. And what this seems to be telling us is these are fragments from another asteroid which have landed on the surface of Bennu. They're not intrinsic to Bennu itself. So this is, again, like Ryugu, has swept up debris. It's probably been broken up and swept up debris and reformed, picking up bits and pieces from other asteroids along the way. But the main event is the sample grab. This is a picture of the spacecraft. You can see the sample return capsule, sort of Apollo capsule heat shield thing in the middle. And the thing that's sticking out bottom left-hand corner is the touch and go sample head. Like Hayabusa, it's a trumpet on a stick. All the other things are cameras and spectrometers. And the idea is very similar. You reverse down onto the asteroid and you try to blow material up into that trumpet. But the requirement for this touch and go was to have a 10-meter clear area that you could target. And it turns out that there are very few 10-meter smooth areas on Bennu. Here's a picture of the thing for scale. You can see the sample head there. in the lab before it was put on the spacecraft. After mapping the asteroid very carefully, they did manage to find a few areas where this 10-meter circle of relatively smooth, relatively rocky, rock-free material existed. They picked these 4 target areas, and the primary candidate is the one top left, which is called Nightingale. The others were evaluated, but Nightingale was the one that was chosen. Luckily, the engineers had discovered that the spacecraft was performing rather better than expected, so they could control it much more accurately than they had originally thought, which meant that their margin of error for that sample circle could be a bit less than the 10 meters that they'd originally expected. So they spent quite a lot of time doing low flybys over these sample sites before they picked the best one. And then in October last year, down they go. And this time I do have a movie. So here's the tag SAM, that trumpet on a stick. The satellite, the spacecraft is lowering itself down on towards the surface, touches the surface, and it ejects material by blowing nitrogen gas rather than firing a bullet. And this is the team in the mission control when they first get the results that make it look like they indicate that everything's worked. So here we go, down we come. Quick adjustment, bash into the surface, dust and gas fly everywhere. Some of that is just thrown up by the impact. Some of it is caused by the thrusters as the spacecraft reverses away. Now, because the movie's quite rapid, you don't see the full detail, but actually the sample head goes half a meter into the surface before it starts to come out again. So that's telling us that's more than a foot. So that's telling us again that the sample is that the surface is not solid at all. It's quite uncompacted. It's quite fragile. Now you may remember that shortly after the the euphoria about the successful touch and go, there was some concern that the material was leaking out into space. Here are some pictures taken. It's just the same 3 pictures repeating, which seem to show material actually escaping from the sample head. And I struggled a bit to understand what was going on until I found this movie. So here's how the sample, the tag SAM goes down. This blast of nitrogen gas is fired into the surface. It picks up dust. It blows up these 2 little red flaps. The dust is blown into the sample container, and then these red flaps are supposed to close again. What seems to have happened is, possibly because it hit so deep, it stirred up not just dust, but also some stones, and those stones got jammed in the flaps and stopped the flaps closing properly. And that in turn led to some of this dust leaking out again. Now I'm just going to go back one. So that's what's happening here. The flaps haven't closed properly and some of the dust is flying out. Now this immediately creates a concern because obviously they've gone to all this trouble to get the dust and they don't want to see it all leak away. Now their original intention, and this is a measure of how clever these engineers are, the original intention was to set the spacecraft spinning and measure how much its moment of inertia had changed. And from that, they could estimate how much material they'd swept up. Now, they were only expecting to pick up 50 or 60 grams. So if you think about the engineering that's required to measure the angular momentum of the spacecraft before, and then measure it again afterwards and see how much different it is, and see if that can be accounted for by 60 grams of dust. But they decided that since these flaps obviously hadn't closed properly, spinning it up would run the risk of spilling the material out again. So they abandoned their attempts to estimate how much stuff was in there and just assumed that it must be pretty full because otherwise the flaps would have closed properly. And having made that decision, they then decided to dock the sample head as quickly as possible to stop any more stuff leaking out. So this is an artist's impression of what happens next. The tag SAM maneuvers the sample head and drops it in the return capsule, which then closes and wraps around it. And what you have is, again, a re-entry capsule that looks a bit like an old-fashioned Apollo capsule, only much, much smaller. So where are we now? After the successful sample grab, there's only there was enough consumables for 3 attempts, but they only had 1 sample bucket. So having had a successful sample grab at the first attempt, they decided not to try again. And they parked the sample container in the re-entry capsule. And since then, the spacecraft has been allowed to drift away from Bennu. And you might think, why? Why not keep measuring? Well, you know, it's job done, really, isn't it? But they made a decision quite a few weeks back that they would do one last thing. The return window to Earth is already open. In fact, it opened in March. What they're going to do is they're going to make a final close flyby on or about April the 7th, so in about 5 days' time. And they're going to return to a point a couple of kilometers from the asteroid, and they're going to hover there for 7 hours or so while the whole asteroid rotates underneath them, and they can do a complete surface map, repeating the maps that they made before the sample grab. And if you think about it, the reason's obvious, quite clear from the sample grab that stuff got flung up and bounced around in all directions. So what they want to do is to map the landing site and see what's changed. And I guess from that, they will be able to determine the local gravity field and the density of the different materials which have been blown up by the sample attempt and have then subsequently fallen back onto the asteroid. Assuming, of course, they're only doing it once. It's one of these risk things. I guess they don't want to risk breaking the spacecraft at this point by doing anything that's too risky, but they've done this before, so they know they're pretty confident they can do it safely again. But they're just going to make one flyby next week, and then they're going to bring it home. So the spacecraft will leave Bennu in about a month's time. It will take 2 years to get back. The sample so the spacecraft is pointed straight at the whole thing is pointed straight at the Earth. About 4 hours before impact, the sample return canister, that's the little ice bucket Apollo capsule with the sample in it, is jettisoned, and the spacecraft then will fire its motors to maneuver into a different orbit so that the spacecraft itself doesn't crash into the Earth. The return capsule then enters the atmosphere in the good old-fashioned Apollo style with a heat shield and all the rest of it. And then it pops a parachute at 30 kilometers or so, and it lands by parachute in the Utah desert in September 2023. Now, I'm not sure what they're going to do with the mothership. I can't imagine they're going to give it up. I should imagine that, as with Ryugu, if the instruments are still working and the cameras aren't covered in dust and so on, and we'll know that because of this flyby next week. But if the instruments are all still working, or in reasonable shape at least, my guess is they will try to then use whatever fuel is remaining to fly off to another asteroid target, as is being done with Ryugu. After all, you've gone all this trouble to build this thing, put it in space. You might as well get the most out of it. But that'll depend on exactly how the Earth flyby goes and how much fuel they've got left and what targets are available once that's been done. But the main concern at the moment is to get back to Earth and to get the material back. And I think that's the end, pretty much. Yeah, that's pretty much all I wanted to say. It's been a fantastic achievement, both of these missions. I am particularly impressed with the Hayabusa mission. The Japanese Space Agency budget is tiny compared to NASA, and yet they've made this rendezvous. They've dropped these landers. They've moved the landers about. They've grabbed samples. They've fired a bullet into the surface. They've grabbed another sample, and they've got it safely back to Earth. It's absolutely terrific. And I think the Osiris-REX sample will have, I suspect, a much larger sample. And so if all goes well in 2 years, that sample will be back on the Earth in the laboratory being analyzed as well. So that's really great stuff. And we can just hope, I hope that Hayabusa does manage to make those other rendezvous in the next few years, because those targets are very interesting. And 10 years from now, I certainly won't be working, but I'll be very interested to see what a 20-meter rotating asteroid that spins in a few minutes looks like. So that's me done. I guess I stop the share at this point.
Thanks, John.
I reappear and I will attempt to answer questions if you have any.
Well, first of all, John, thanks. Fascinating. We covered these missions when we could all meet together. I remember covering both of these in the news. I think when they were launched. So it's really nice to see some progress reports and conclusions. Can we thank John in the normal way, please?
Thank you very much. Here is my model of.
Excellent, excellent. Questions in the normal way. I know Peter's put it out. If you're on Zoom, put it in the chat line. Peter will ask you to ask them. If you're watching live on YouTube, you want to ask a question, then put it in the comments section. We'll try and capture a few of them. So over to you, Peter.
Okay, great talk, John. Loved it. Really good. The first question was from John Murrow. John, do you want to ask your question?
John, I can see it in the chat actually.
All right. Okay.
Why do they use copper from the impactor? You know, that's a good question, and I don't actually know the answer, but I know that they use copper on this, and they also used it in the deep impact experiment to throw a lump of rock to throw something at Comet Tempel, the nucleus of Comet Tempel 2. So I suspect the answer is that it's not something which you would expect to find naturally on these objects, and therefore, if you get some signal from copper in your spectrograph or whatever, you know that it's from your impactor and it's not intrinsic to the asteroid itself.
And then we've got Nigel.
So Fred,
this question actually.
Yeah, so this is Fran and Nigel. Does that not contaminate the asteroid? I guess it does a bit. Does it not matter? Well, I guess it does a bit, but I'm reminded of a line in 2001: A Space Odyssey, where the spaceship flies past and fires a laser beam at an asteroid to vaporize some of it. And then some cynic says, well, why don't you throw an atom bomb at it and photograph the debris? So yeah, I guess it does contaminate the asteroid a bit, but I don't suppose it does really matter, because it's not like Mars where there's a danger of contaminating it with life. Why is the battery? Neil Martin asks, why is the battery life of the landers so short? I think in the case of Mascot, it was because in all of these things, it's a sort of an engineering trade-off. Batteries are simple and reliable. Solar power systems are less so. I mean, look what happened with Philae. Philae had solar panels, and by chance it landed in shadow, so it couldn't recharge its batteries. So I think it's an engineering trade-off where you say, what do we want, and can we get it in the time that we can run on batteries? And if so, we'll use batteries because they're reliable and so on. So that would be my guess. I mean, the Apollo lunar lander used batteries for the same reason. That they just worked out how many amp hours they needed and how much the batteries would weigh, and that's why that was the way they decided to go.
Tim? Fire away, John.
Oh, so Tim asks, is there a set criteria for which asteroid they chose to explore? There is actually, if you look at the Osiris-REX web pages that you can find, I mean, just by Googling Osiris-REX, they actually show how they make this decision. And it starts off with how much money have we got? How big a rocket can we afford? With that, how much delta V, how much acceleration, so total acceleration can we get? With that, which asteroids are in range? With that, which asteroids can we reach and get back? With that, which ones are there and how do we, and then which ones are the most interesting? So there is this huge decision pyramid where there are hundreds of asteroids in principle, and you very rapidly come down to a handful. And so you, first of all, you have to take all the engineering constraints in, and then you ask the question, well, has an asteroid of this type been visited before? Meteorites that we find on Earth are fragments of asteroids, so it makes sense to go to an asteroid which isn't well represented in our meteorite collections, because ironically, as you may well know, a meteorite landed in Britain only a few days ago, which turns out to be of a very similar spectral type to Ryugu. So the Japanese went to all this trouble to get a few grams of this material. And somebody in Lincolnshire or Leicestershire or wherever it was had a lump of it land on his driveway in the middle of the night for free. So yeah, there is a very complicated decision tree, and it's a good read. If you look at that page on the Osiris-REX webpage, I think I actually grabbed it and made a slide of it once, but I didn't show it. Emma asks, is the ejection of material the reason they are less dusty and more rocky than expected? No, I don't think so. I think I don't think it's a question there was a lot of dust and it's all been blown away. I think they are more rocky because of what we've learned about their formation, that they've been smashed up, reassembled, and in that process, all that you get left when the thing reassembles is an aggregate of boulders. And thank you to John, who says it landed in Gloucestershire. Sorry, I knew it was somewhere in the UK. On somebody's driveway. The Barwell meteorite also landed on somebody's driveway back in the 60s. Okay, meteorite's not my field.
Okay.
Tim asks, isn't that the one that caused a daytime sonic boom? Quite possibly. But it's just the irony of this thing coming free when so much trouble had been gone to get a sample.
Well, thanks very much, John.
Well,
who's handling YouTube tonight?
Let me just say hello to Clive and to Alan, buddies of mine from the observatory way back when.
Oh, yeah.
Hi, John.
Will, are you doing the...
Yeah, we've got a few questions from YouTube here. That was a wonderful talk, John. Really exciting. First of all, we've got one from Chris Ryan. How far are we from the age of space mining?
Yeah, indeed.
I know it's a big look into the future, but it's got to be on the cards. It's got to be talked about sometime.
Well, further than we think, I suspect. I mean, it was a sort of thing that people talked about a lot in the 70s. Gerard O'Neill and his L5s. But there's a paradox here, which is that, you know, platinum is expensive because it's rare. If you found an asteroid which was made of 500,000 tons of platinum, and you were able to land it somewhere in the Sahara Desert, let's say, platinum wouldn't be worth anything because there'd be so much of it, it wouldn't be valuable anymore. So the whole economic argument for getting it in the first place would disappear as soon as it arrived. So I don't actually see space mining as a big thing until we're really building large structures in space. When you're really building large structures in space, there will come a time when it makes more sense to collect the material locally than blast it off the Earth's surface. But I personally don't think it's anything anytime soon.
Thank you very much for that. And we've got a question from Asteroids Physics. He just asked, what's the weight of this sample from Bennu? Do you know what the weight of the sample was taken?
The requirement was a few hundred grams.
Okay, so it was very small, very small.
Yeah, so we're not. Yeah, it's a few hundred grams.
And finally, we've got one from actually Stephen King. Do these objects have any color at all? We always see them as grey and such, but is there any way of seeing any more color on them, or is it just the dust and stuff which is giving the grey color? Okay,
so the good question. I just thought about something. The question before said how much is it? 200 grams. Okay, 200 grams is a small packet of licorice all sorts. It doesn't sound like very much, but with modern technology, modern instrumentation and mass spectrometers and that sort of thing, we can get a fantastic amount of information out of 200 grams of material. So it doesn't actually sound like very much. You know, it's not even a flower pot, but it's a lot if you put it in a lab with lots of fancy equipment. Sorry. So the other question was, why is there much color? Actually, they're very dark. I had a note of that and I forgot to say it. The reflectivity of the Japanese target is only a few percent. Coal is quite shiny compared to this stuff.
Right.
So they are largely grey. And astronomers, of which I am one, willfully talk about asteroids being red or blue, but actually we just mean they reflect slightly more red light or slightly more blue light. They are all pretty much dark grey. So yeah, they are, even the bright ones. Well, the Vestoids, I think, have a reflectivity of about 30%, so they are surprisingly shiny. But stones have a 10% reflectivity, and the C-types is like about 3%, 2%. So they're really quite dark.
Well, thank you ever so much, John. Can we show our appreciation again, please? Excellent. And perhaps, John, we can book you once the analysis has been complete and you come back and finish the story.
Oh, that's very kind. Yes, I did have a quick look around to see if I could find any results, but it's a bit early for the Japanese ones yet. Give them time to get their analysis and their papers published.
Brilliant. Thank you very much indeed. We're going to move on now, and Ian Smith is going to talk to us about the sky in April. So I'll let you share your screen, Ian.
Okay.
And thanks once again, John.
Okay, is that coming through okay?
Yes, it is.
And can you hear me okay?
I can hear you fine.
Because I'm limping along on a very quiet microphone.
It's excellent. Thank you.
Good. Okay. Well, a very brief report for April, the night sky. And I'll start by explaining that since Christmas, we've come 90 degrees roughly around the orbit. And as we move around the sun, we're now in the spring equinox, and it presents to us a different view of the universe compared to that of the winter solstice. So that gives us a different view since a few months ago. And Alan Pickup has kindly put together the views looking north and south. And the night sky shows the positions of the constellations. The visible planets are quite low at the moment. The Moon and Venus will appear close together on the 12th of April, and the Moon and Mars will appear close together on the 17th of April, but both encounters will be close to the horizon. We have later on in the month the Asteroids meteor shower, which peaks on the 21st to the 22nd of April. The moon, unfortunately, will be about 65% illumination, and that will make the fainter meteors harder to discern. The dust that causes the shower comes from Comet Thatcher as it travels around the sun. And you can see there the Lyrids appear to come from an area just to the right of the constellation of Lyra, and just to the left of Hercules. There's also a comet, C/2020 R4 Atlas, and it will be at its closest approach to Earth in April. This will happen on the 23rd of April, and it's currently calculated that it will be close to the constellation of Corona Borealis, and it will probably require a telescope to observe unless it becomes significantly brighter. So that's it roughly there between Corona Borealis and Hercules. Another thing that's maybe possible to observe is the zodiacal light, which is visible in springtime towards the west, up to an hour after dusk. Current thinking is that it's light scattered by dust that has escaped from Mars or its moons. Viewing from a dark site will definitely be required, unfortunately, where I am, the lights from Haddington will obscure the view. But can always go out into the hills, I guess. And we've got a supermoon coming up in April. And it's traditionally called a pink moon, but of course it won't be pink. And it will look just like the one that Mark Phillips has photographed to the left. It's referred to as a supermoon because its orbital distance from Earth is at a minimum, or perigee, should say. This will occur in the early hours of the 27th of April and setting just before 6 a.m. And it's sometimes referred to as galaxy season because the galaxies at this time of year ascend the night sky, which makes them easier to observe. And here are a few examples of galaxies taken by members. And this is the Pinwheel Galaxy, or M101, by Mike McGovern. There's the Needle Galaxy, or NGC 4565, by Pat Devine. There's the Whirlpool Galaxy, M51, taken by Mark Phillips. M106 by Nigel Goodman, and Bode's Galaxy, or M81, taken by myself. So galaxy season. There also appears to be an online festival called Worldwide Astrofest, which will be taking place online at worldastrofest.com. I found 2 events in April: Astronomy Under Threat on the 8th, and Dr. Brian May of Queen fame will be talking about viewing the universe in 3D, which sounds interesting. If you'd like to read further into the effects of satellites on the night sky, of course, then Professor Andy Lawrence has recently published a book called Losing the Sky, and it even has a foreword from the ubiquitous Dr. May. So that's the end of this, as we all descend into NASA's depiction of a black hole.
Excellent, Ian. Thank you very much.
Okay, thank you. I can figure out how to unshare.
We are looking for anybody else who wants to have a go at giving us the night sky one month. And
We've just got that book.
And
Yeah,
next month we, oh yes, I see the book. Well done, John. And Alan will be doing the night sky next month. Thank you very much, Alan. Okay, well that really brings to an end tonight's events.